Hello guys, in this video we'll gonna prove this lemma for a metrizable space, that is given a metrizable space and an open covering for x, there exists another open covering xi of x which will refine our given open covering and it is countably locally finite. So let me first give you an example of this statement. What does it mean? Then we will prove this lemma. So let me first give you an example. Suppose we have R with the usual topology, with the tau usual. All of you know that this is a metrizable space, which is whose topology is generated by the usual metric. This is metrizable, and let us choose an open covering, and then we will construct another open covering which will be refining of that open covering, and that will also be countably locally finite. So let us choose this covering for R. Let me denote it by B, or let me denote it by A. Let us choose this given covering n plus 2 n belongs to z where z is the set of integers. Since in the previous video I already proved that this is a countably locally finite because it is countable collection, we will simply try to refine it. Let us denote B by this collection n plus 3 by 2, where n is in our in our set of integers. Clearly this collection B will refine A, and since this is countably locally finite, we don't need to find covering for this in order to construct another open covering such that which is locally finite. Since it is already locally finite, we no need to construct another covering, but there is another covering B which will refine A, and it is also countably locally finite. You can check it easily that this is an open refining for this collection A. Let me briefly describe it. That our collection was 0 2 1 3 dash dash, and in our new covering we simply chose 0 and 1 and 1 half, that is 3 by 2, this element, and another element will be look 1 this, and it is 4, then another element will look like this, and therefore for each element we have an element in the covering A which will contain this element of B. Therefore this B is the open refining, and each of the element in B is open set, therefore this is open refinement of A. So let us come back to our lemma, that is we have to prove we have given there is a metrizable space and an open covering. We have to construct another open covering which is refinement and also which is countably locally finite. So in this term, by open covering we simply mean that in the covering we have open sets, that is if X is metrizable and we have chosen some open covering, that is these are the sets, these are the open sets in our covering. These all are open sets, and their union of all U gives us X. X is contained in union of all these U where U belongs to our covering A. This is simply what we mean by open covering. In order to prove this theorem, we will use well-ordering theorem. So we will use well-ordering theorem, which was proven by Zermelo in 1904. I assume that you have gone through this theorem, the statement, at least the statement of this theorem. Well-ordering theorem, which simply states that given any collection of open sets, there exists an ordering with respect to which the collection is well ordered, or that set is well ordered. That is, it simply states that if we have a set A, there exists an ordering with respect to this ordering, this A is well ordered. This A is well ordered. Well ordered simply means that every subset of A has the smallest element. So you should go through the statement of this theorem, and we will use this for our collection A, that we will assume our collection is well ordered by some relation which we represent by this less than sign, although this doesn't mean less than, but usually we represent ordering by this symbol. So what we will do, since X is our metrizable space, we will choose some metric. We will choose some metric D, which will generate its topology, which is clear. And our covering is given this symbol A. Let me choose any element U in this covering, which is open set as well. What we will try to do, we will simply shrink its size. If we have this set U, this is our U, which is open. We will simply shrink its size by some amount, and we will use our well ordering theorem in order to pass to a smaller set. By using well ordering theorem, we will pass to a smaller set, that is, we will still get a smaller set out of this. Then we will simply expand it a little bit, and we will take the union of all those sets, and we will prove that it is an open refinement as well as this is covering. So how we are going to do this? We will simply choose element in this open covering and fix some integer, suppose n, and let us for sake of convenience, let us fix 50. Let us fix integer 50. Now for this U, what we will do, we will simply, this is our U, we will shrink its size by 1/50. How we will do that? We will simply consider the set, let me denote it by S50 of U, which will consist of all elements X, such that if we consider ball around X and of radius 1/50, it should be contained in our U. That is, S50U is simply the set of all elements in U, such that when we choose a ball around that point of radius 1/50, it should be contained in our U. This was our U, and what we will do, we will simply shrink its size by 150 from all over. That is, this will be our S50 of U. As you can consider here a point and choose a ball of radius 150. Then since this ball is contained in U, therefore this point will go into our set S50U. And similarly for all these pointers, since U is open, we can choose this. And also this boundary will be included in our set S50, as you can choose here a point and a ball of radius 150 here, because this distance is simply 150. This distance from all sides, this distance is 1/50. Therefore if we choose a point here on the boundary, then we can choose a ball of radius 1/50, which will be included in U. Therefore this boundary will also be included in this set S50U. Therefore it will be a closed set. Now we will use our well ordering theorem in order to pass to a smaller set. And let me do it geometrically for some elements in our collection A. Let us choose 3 elements from this, and geometrically we will do it. Let us choose U, V and W in our collection A. And since our collection is well ordered, therefore let us assume that U is less than V and V is less than W. So we have a situation like this. This is our U, this is our V, and this is our W. Let us suppose. First, what we did, we simply shrunk the size of all these members by let us say 50, by 1/50. We choose our integer to be 50. Then later on we will generalize it to the n. We choose our distance to be 1/50. The integer we fixed was 50. So our next situation will look like this. This U was shrunk by a size of 1/50. Therefore next set we will get will be like this. This we represented by S50 of U. This was our S50 of U. And similarly we will shrink this size, this V, up to a size of 1/50. Therefore this will be our S50 of V. And similarly for W, we will also shrink its size by 1/50. So this set will be over S50 of W. Now we will pass to a smaller set, smaller collection for these 3 sets. What we will do, we will simply from S50 of all these sets, we will delete or remove the portion which is in their common, which is the common portion between all these sets. That is, we will define another collection. Oh, I have to rub this, I am running out of space. We will do this thing as we will define another, let me define T50 of U by S50 of U. From this S50 we will simply remove union of all those sets, all those B sets in our collection which precede B, which precede our U, such that B is less than U. And therefore for these 3 sets we will have a situation like this. T50 of U will be, I will also show this geometrically. Let me first write it. U minus, since U was less than V was less than W, and there is no set which precedes u, therefore this set will be phi. Therefore T50 of u will be simply S50 of u, and T50 of v will be simply S50 of v minus u, as u precedes w. And what will be T50 of w? T50 of w will be simply S50 of w minus union of these two, as they both precede w in the ordering. So we will have to remove this portion union u, and we have to remove u union v from S50 of w. So let me show you how this. So this was our u, this was our v, this is our u, this is our v, this is our w. From u we shrank its size by 1 over 50, therefore we got this set. We got this set S50 of u, and we got this set S50 of v, we got this set S50 of w. Then we, by using well ordering, we still pass to a smaller set. Let me show you. This was our S50 of u, this was our S50 of v, and this was our S. Since u nothing precedes u, therefore this S50 will be same as T50 of u. T50 of u will be same as S50 of u. Now since u precedes w, v, from S50 of v we have to remove the portion u. That is, we have to remove this portion, and the remaining set will look like this, and we have to remove this portion. Therefore this will be our T50 of, this will be our T50 of v. And from w we have to remove the union of both of u and v from S50 of w, therefore we will remain with this portion. So this is our T50 of w. This portion is our T50 of u as well as S50 of u. This portion is our T50 of v, and this portion is our T50 of w. And from the figure it is clear, since this distance was 150, since this distance was 1 over 50, this distance was also 1 over 50, and this distance was also 1 over 50, this distance was also 1 over 50, this distance is as well 1 over 50. It is clear from the figure that these three sets will be disjoint. These three sets, that is T50u, T50v, T50w, will be disjoint, and at most their distance will remain 1 over 50. That is, the distance between all these three sets will remain at most this much, which is clearly 1 over 50. This much, this will remain, this distance, this distance, this distance is 1 over 50. Therefore if we have any point here and any point here, the distance will be larger or equal to 1 over 50. That is for any x and y belonging to if we have x belonging to Tn of v, y belonging to Tn of w, distance between them will remain at least 1 over n. It is clear, it was clear from the figure that distance will remain at least 1 over n in general, and in our case we choose our positive integer to be 50, therefore it will remain at least 1 over 50. Now since it is clear that our t and v's, they are still not the ones we want, they are still since we need the open refinement, but they are closed sets, so we will have to do some trick in order to obtain open sets. So what we will do, we will simply now expand them by a little bit. We will simply expand by them those by a little bit. Let me show you how we will do that. This was our u, and this was our v, and this was our w, and we simply shrink this by 1 over 50, and then we removed the portion of those sets which precede the next one. This was our S50 as well as T50, and then this portion was our T50 of E, and this gap was 1 over 50. This gap was 1 over 50. That is, they were 1 over 50 apart. Now what we will do, since these are the closed sets, this is closed set, this was T50 S50 of U, which is same as T50. This was a closed set, which was clear because its boundary was also included. This was a closed set, but what we need open sets. So what we will do, we will simply now expand all of these by one third of this distance. Since the distance between them is 1 over n or 1 over 50 in our special case, we will simply expand them by a little bit. That is, if this distance is let me show you here. If this distance is 1 over n, this was over 1 over n, this distance, what we will do, we will do three divisions of this. So this will be 1 over 3n, this will be 2 over 3n, this will be 3 over 3n. So we will expand all of these sets by 1 over 3n. Therefore the sets we will get, let me represent those. We will simply, although it is much difficult here to show, let me still try to represent. That is, we will allow them to expand by 1 by 3n distance, all of those. We will expand all these by 1 over 3 distance. And let me represent these sets now, that is these sets, that is these sets, this much, this 1 by 3n we involved in our set by expanding our T and T50 of W, this much, and this is also now included. And from the figure it is clear that still distance remains this much in between, which is 1 over 3n. this distance will still remain in between them. This is our En. So this distance will still remain in between, this much and this much, which will be 1 over 3n, which is clear from the figure. We can also prove it by using the triangle inequality. So what was our En now? How we defined En or E50? I think I will generalize now this En. You got the idea how we do this. En of U was simply, we expanded it little bit, our Tn50, that is, we consider this the union of all the balls centered at x of radius 1 over 3n, where x was in our Tn of U. That is, En was simply generated by these balls of radius 1 over 3n, where their center was in Tnu, which is the mathematical description how we expand all those sets. So En of P was simply union of all the sets of the union of all these balls. Let me denote it with center y 1 over 3n, where y was in Tn of V, and similarly En of W is defined similarly. It is clear still they are disjoint and 1 over 3n apart. That is, if we have disjoint sets U and V, and if we consider any 2 points x in our E and U and any point in E and V, then it was clear from the figure that distance is still 1 over at least distance is 1 over 3, and it may be larger than this. I think you can simply prove it by using the triangle inequality. So or let me show you how we are going to do this. Since x is in our A and U and y is in our A and V, which implies this must be in some ball of with center some z and distance radius 1 over 3n. That is, if we choose x in E and U and y in E and V, and we are here assuming that U and V are distinct from the A, from our collection A. So x will clearly be in some ball with center z and radius 1 over 3n, because En is simply the union of all these, and y will also be in some ball of let us suppose with center T and radius 1 over n. Let me show it geometrically. This is our ball with center x and radius 1 over 3n, where z, our center is z, and this is some point x in this ball, and this is our x, and this is our another ball and with center T, and here is some point y, and this is also this much distance 1 over 3n. Since z and t are in Tn of U and Tn of V, we already showed in the previous figure that distance between z and t must be at least 1 over n. That is, we have to show that distance between x and y, that is this much distance, this distance is greater or equal to 1 over 3n. But we know that this distance is greater or equal to 1 over n, because z belongs to, z is in our Tn of U and t is in our Tn of V. Therefore, distance between them must be greater or equal to 1 over n. This much distance is 1 over n. this is 1 over n. It is clear from the figure that the smallest distance between x and y will be if x is here and y is here. Otherwise the distance will be bigger than this distance. If x is here and y is here, then this will clearly be greater than this distance. Now let us figure out how much distance is this much. This distance, let us figure out how much it is. Therefore we had, this was over z, this was over t, and distance between them was 1 over n, and the smallest distance between x and y was when this is on our this is just touching the boundary x of this ball, and y is simply also touching this boundary y, and clearly this is over 1 by 3n and this is over 1 by 3n, and clearly distance will be between x and y will be greater or equal to, distance between x and y will be greater or equal to 1 over n minus 1 over 3n minus 1 over 3n, which is simply 1 over 3n, which is clear from the figure. So now we will choose our covering. We will simply take the union of all these sets which we got after expanding our TNUs and TNVs and TNWs by a distance of 1 over 3n. So we will define xi n to be collection of ENUs, where U is in our given collection A. But this xi n will not cover whole of X. Although it is the refinement, it is open refinement, because clearly ENU is contained in U, which was clear from the figure. ENU is contained in U for each n, for each U. Similarly, ENV was contained in V, ENW was contained in W, which clearly gives us that xi n is the refinement. And we will also prove that this is locally finite. This xi n is locally finite for each n, it is locally finite. Then we will take the union of all these locally finite collections, which then we will show that the given collection is our covering for X. So let me show this geometrically first, how they are contained in each U, V, W, and then we will show that this is locally finite. Although it was clear from the figure, we simply took first U, V, W, then we simply shrunk their size by 1 over n, then we simply defined Tn by removing the portions which were preceding the others. We got this figure, we got this figure. This was our, since U was preceding all of, this was the first element, therefore Sn of U coincides with Tn of U. But from this we have to remove this portion. This we got, this is our, and clearly that all of these and then we expanded them by a little bit. We expanded, since it is a bit difficult to draw it clearly here. We expanded them by a little bit, 1 over 3n distance each of those, and they will still remain in each these U, V, W's. It is clear that EN U is contained in U and ENV is contained in V. Therefore this EN V is the refinement. Now we will show that this is countably locally, this is locally finite. Now how to show that? If we choose any point x in our X, we have to construct a neighborhood which will intersect only finitely many of these sets. that is this must we have to construct a neighborhood around this x. We have to construct some ball some radius x, of some radius r, such that intersection with xi n must be finite. That finite in the sense it should intersect only finitely many elements from this collection. Now let me show you how we will do this. We will simply construct a ball of radius 1/6n around x, and let me show you it will intersect only, at most it will intersect one element from this collection. Since our en u's and en v's was this, let this be x, x was chosen, this is z and this is y, and we know that the distance between them is 1/n, and this was over 1/3n distance. This much distance is 1/3n, and this was over 1/n distance. Now if we choose a ball of radius 1/6n at some point, our x may be anywhere here, because this x originally is in our space x. So x may be here, x may be here, x may be here, it may be anywhere, it may be in between. So if we choose a radius of a ball of radius 1/6n, which will simply this, it will clearly intersect only this ball, because this ball is clearly disjoint from this ball. So if we choose this a ball of radius 1/6n, it will be simply it will intersect only this ball. And if we choose a ball here, if x is here in between, then it will not intersect any ball at all. Therefore intersection is also finite, because this much distance is 1/3n. If we choose a half of that, this will be our 1/6n distance, and we choose a ball of radius 1/6n, it will clearly not intersect this one, neither this one. Therefore at most a ball around x of radius 1/6n will intersect at most one element of xi. At most it will intersect to one element. Therefore this is locally finite, this collection is locally finite, which is our xi u, which we denoted by xi. It was the collection of all en u's such that u was in our given collection A, which clearly shows that this is locally finite. But still this xi n doesn't cover our whole of x, as was the clear, because let me show you another time there, because clearly this much portion was left in u, this much portion, this was our t, and then we simply further reduced it, then we expanded it a little bit, we got this much we got, but still this portion was left. So since our u is not covered, so it is obviously that our collection xi n will also not cover whole of x, because u is not covered, so u is simply a subset of x, so x will also will not be covered by this collection. Now but what we will do, we will take the union of all these collections, then we will show that will simply cover our x. That is, we will simply define now xi to be union of all these n where n belongs to n. Now we will show this is exactly cover of x, and since each of this is locally finite, for each n this is locally finite xi n, their union is countably locally finite, because union is taken over n, countably locally finite, and which will prove our claim that every metrizable space and a given open covering, there exists an open covering which is countably locally finite and which refines that covering A. So now the remaining portion of this lemma remains that we have to show xi is a cover. So for that we will simply show that X is contained in our xi. So we will take any point here, we will show that it also belongs to xi. So let me take any point here in X, our space. Since A is the covering of X, that is union of A, where A in A, X is contained in this covering. Therefore this X must be in some element of this covering, that is X must belong to some element U which belongs to A, since A is the covering. Since A is well ordered, we also need well ordering. Since this is well ordered, let this U be the first element in that ordering which contains X. This be the first element in that ordering which contains X, that contains X. That is, if we have some order over the elements of A, let me show like this. We have some order, and let U be the first element. This be the first element in which this X goes, because X must belong to some of these elements. Let this be the first element where X belongs to. Therefore what we have, since U is also open in X, therefore there must exist, we can simply, also this is metrizable space, we can construct a ball around X. Let me show you here. This is our U, which is the first element in that ordering which contains X. Therefore around X we can construct a ball of radius 1 over n such that which is contained in U. That is, we can construct a ball of radius 1 over n, X belongs to this which is contained in U, which simply implies then X will belong to Sn of U, because Sn of U was the collection of all those elements around which we took a ball of radius 1 over n such that which is contained in that set. Therefore X will belong to Snu. Since also U is the first element in that ordering which contains X, therefore Snu will also coincide with Tnu, which is clear, because we don't have to remove any of the elements from Sn, because U is the first, which clearly implies that X belongs to Enu as well, because En is simply obtained by expanding this. If X belongs to this element, it will also belong to Enu, because this is a larger set than Tn of U. And since X belongs to En of U, which simply implies X also belongs to xi n. Xi n is clearly the collection of all these sets En of U, where U is in our open covering A. Therefore X belongs to xi as well, because xi is union of all xi n's. Hence our X is contained in xi, which implies xi is covering. Hence we were able to reduce this cover, we were able to reduce this to xi, which is countably locally finite, which is countably locally finite. Yes, this was our claim, and which is also the refinement. Also this is open refinement of A, because each of its elements has a corresponding to each of element of this xi, we have an element U here corresponding to each xi element. Here we have an element U here which contains its element. Therefore this is an open refinement of A, which was our claim. So let us summarize what we did. in the previous lecture. And this, in the previous lecture we simply introduced the concept of countably locally finiteness. Since we were determining the conditions for a topological space to be metrizable, and we also know that every metric space is first countable here, first countable, every metric space is first countable. This you all of know, this you all of aware of. And for our topological space we choose regularity and countable basis here, which gives us the metrizability condition, sufficient condition for the metrizability. But in between, somewhere here, I don't know where it lies, we introduced the concept of countably locally finiteness. Now we show that every metric space should also satisfy this condition. Every metric space should with a given open covering should satisfy this condition, that its basis must be countably locally finite. Its covering must reduce to an open refinement which is countably locally finite. Now if a topological space is metrizable, then this becomes the necessary condition. This condition becomes the necessary condition for that metrizable space in order to satisfy this. Since first countability is also the necessary condition for a metric space, therefore every topological space which is metrizable should necessarily satisfy this first countability. But this was not our necessary, this countable basis. Therefore this countable locally finiteness gives the exact condition for a regular space to be metrizable, which was proved by the Nagata and Sumeno in the metrization theorem. This is all about this countable local finiteness, and maybe in the future lectures we will prove. I also there remains to prove the inverse for the Eurytion metrization theorem. There remains to prove that F inverse is continuous also, which I haven't yet proved, but I will prove it in near future lectures. And also we will do some theorems in the functional analysis portion. So thank you. If you like this video, kindly share it to your relevant friends. And if you are having problem in any kind of concepts I described it here, let me know in the comments. Thank you.